Okay, so this problem is from page 116. It's number 42. You can use it to answer number 5 of Dr. Padgett's exam 3 problems. Calculate percent ionization of formic acid solutions having each concentration. So we'll start with 1.00 molar. So let's take a look at what we're dealing with, formic acid. So if you don't know anything about formic acid, you can already kind of deduce a couple things. If you don't recognize it, or it's, it may not be in your strong acid list that you had to memorize, and it's not in your strong acid list. So therefore, it's a weak acid. So it's a weak acid, and we're not given Ka. So for this problem, you'll have to go seek the Ka in a table, or you could Google it, and you'll find it to be 1.8 times 10 to the negative 4. So also what's true about weak acids and weak bases is if you want to find their concentration, or if you want to find their pH, or if you want to find percent ionization, you'll have to use an ice table or a rice table. So our rice table will look like this. R stands for reaction. So we have to write a line reaction for formic acid. But we don't know what formic acid looks like, so what should we do? Well, we know that an acid will give away a proton. So I'm just going to go ahead and write that proton right in the front. And I'm going to abbreviate formic acid with Fa. So this is going to be my formic acid. It's going to be aqueous, because typically acids and bases are in aqueous solutions. Aqueous meaning it has water. So that's the liquid part. We'll go back and forth. And an acid dissociates. It gives up a proton. So I will show that proton being given up. So if this is neutral, then it without the proton will be -1. And where does that proton go? Well, it's donated to the water, right? So now water has an extra proton, and therefore it's positively charged. All right, so now what do we have initially? For A, we have 1.00 molar. Water's in the liquid phase, so we ignore it completely. It's not in our ice table or mass action expression. We have no formic acetate or formic acid anions, and we have no hydronium ions. We know that some of it will ionize. We don't know how much, but if it does ionize, what that means is the H is going to be removed, and therefore give this a negative sign, becoming an ion. So we don't know how much that is. We'll note it as X. And we know that the ion is now over here on this side. So it's the same X that's being removed that's being added to both sides. Okay. So our equation, our equilibrium expression is 1 minus X, X. We could use this table to make a mass action expression. So our mass action expression is going to be Ka equals our products, which is Fa minus, over our reactants. And now we can plug the values in. 1.8 times 10 to the negative 4 is x times x, so x squared, over 1.0 minus x. Now, to evade the quadratic formula, we have to assume this x is small. Now, how does that work? Well, Dr. Padgett uses the expression order of magnitude quite frequently, and what that means is like how many, exponentially, how many decimal points away are you from the original smallest concentration. So what we're aiming for is 5% of 1. So this is 5% of 1.00 molar equals 0.05. If we have a number that's less than 0.05 when we use the small x approximation, we're in the clear. So let's use that small x approximation and not bother with quadratic. 1 times 1.8 times 10 to the negative 4 is 1.8 times 10 to the negative 4 equals x squared. Square both sides, and you'll get 1.34 times 10 to the negative 2 equals x. So that gives us our x, and our x is less than 0.05, so we are in the clear. Now, how do we use our x to find our percent ionization? Well, this x is this x up here, and this x up here. These are the ionized species here, right? Fa minus is the ionized species. So we will take the concentration here, that ionized, and divide it by the original concentration of the unionized species and multiply it by 100. Okay, so for B, we have a different concentration. We have 0.5 concentration. We have half of the concentration of A, so let's see how that affects our percent ionization of formic acid. So I'm going to use the exact same line expression. I'm going to put it in an ice table. I'm going to use the exact same mass action expression. Of course, these values will be slightly different. So let's get started. All right, so initially we have 0.5 molar of formic acid. Initially, none of it has ionized. Then some of it ionized. And so we'll take the initial minus the bit that ionized. And here's the bit that ionized. We'll stick that in our mass action expression here. So Ka equals Fa minus times H3O plus over the reactant formic acid. So to plug in all the numbers, we have 1.8 times 10 to the negative 4. Remember, that's our Ka that we found in the table in our book. Equals x squared. That's x times x times x. Divided by 0.500 minus x. I want to evade the quadratic equation, so we can do that as long as our x turns out to be less than 5% of 0.5. So it has to be less than 0.025. So if we evade it, just get rid of it. So this algebra looks like this. It's 0.5 times 1.8, which is actually I didn't write it down. So 0.5 times 1.8 times 10 to the negative 4 will equal our x squared, and then you square both sides, and you get your x to be 9.49 times 10 to the negative 3. This is less than this, so we're in the clear with the small x approximation. We can use it. So to determine our percent ionization, you would want to set the concentration that did ionize over the original concentration of the unionized stuff and multiply that by 100. 9.49 times 10 to the negative 3, 0.500 times 100. Percent. Okay, for C, you go about the exact same way. You make an ice table and you plug in your numbers, 0.100, 0, 0, minus x, plus x, plus x, 0.100 minus x, x and x. Okay, so here's your mass action expression. We'll plug it in here, 1.8 times 10 to the negative 4 that we got in our table in our book equals x squared over 0.1 minus x. If we want to use a small x approximation, it has to be, our x must be less than 5% of 0.1. And so it has to be less than 0.005. So if I use the small x approximation, I get just under 0.005. So we're in the clear. To find percent ionization, I would take the concentration that was ionized here and set it over our initial concentration of the unionized. Multiply it by 100, and you get 4.24%. Okay, and for D. So we use the same ice table, we use the same Ka that we found in the table in our book. So, that didn't actually change the values, so 0.500. Oops. 0. Okay. So you'll get 1.8 times 10 to the negative 4 equals x squared over 0.05 minus x. And then if you use a small x approximation, you'll get 0.003. And unfortunately, 5% of 0.05 is less than 0.003. So we can't use our small x approximation here. We'll have to go through the quadratic equation. I don't expect most professors to expect you to do the quadratic formula during the test, but in case they do, please memorize it. So you'll take 1.8 times 10 to the negative 4 equals x squared over 0.05 minus x. You'll rearrange that formula. You'll have to multiply the denominator by this, so 1.8 times 10 to the negative 4 times 0.05, and also 1.8 times 10 to the negative 4 times x. So, and then you get them all to the same side of the equal sign. So 0 equals x squared plus 1.8 times 10 to the negative 4 x plus 9 times 10 to the negative 6. And if you can program your calculator to spit out the x, you'll get a plus or minus number. Get the positive number, not the negative number, and you'll have 0.0029 as your x. So to find percent ionization, you'll take 0.0029 over 0.05, multiply it by 100, and you will get 5.0 8%.